In the last video, I discussed about the logistic equation and the threshold equation, threshold model, right? It is similar to the logistic equation. So in the logistic equation, the population grow if the initial population is less than the carrying capacity, and the declines if the initial population is more than the carrying capacity, right? But in case of the logistic with a threshold, in case of the threshold model, the population increases if the initial population is above the threshold value, and the population decreases. And if the population is below the threshold value, then the population goes to the to zero, right? The population extinct, right? So if you combine the logistic growth and the threshold, the model will look like this, where y is the population and t is the time. So ry times 1 minus y over k, and then times y over t minus 1, okay? So if this is positive, if y is less than k, this will say population will grow, but it will decay if y is less than t, okay? So meaning that if the initial population is less than the threshold parameter. So there are so many combinations possible there. So I want to show you how to analyze this model, okay? So what are the equilibrium points here? So the equilibrium points here are, so you set dy over dt equals to 0, you get y equals to 0, y equals to k, and y equals to t, right? These are the three equilibrium points you will see here, okay? Now, I want to check the stability of the equilibrium point. So how do you do that is, first of all, you need to draw the fy versus y, right? Y versus f of y, that is y prime, right? So what are the three equilibrium point? One is 0, right? Another is t, and then another is k, right? 0, t, and k. We see that between 0 and 0, t, and k. So between 0 and t, it was like, we see that, right? And then between t and k, it will be like this, right? So we saw that, because see, if the value of y is between 0 and t, value of y is between 0 and t, so y will be basically less than t, right? If the value is of y is somewhere here, then it will be less than k, obviously, and less than t. So this will be y over k will be less than 1, it will be positive, and this will be y over t will be less than 1. So this will be negative, right? At that time, dy over dt is negative, meaning fy, this is the fy, right? Fy is negative, that's why we have that. And then between t and k, meaning it is greater than t, y is greater than t, meaning this will be positive. So if y is greater than t, if y is somewhere here, and less than k, if y is greater than t, this will be positive. If y is less than k, this will be less than 1, so 1 minus less, so this will be positive as well, right? So positive times positive will be positive, so it will look like this, all right? And then continue that way, all right? All right, so now to test the stability of the equilibrium, what we need to do is we need to see that, look at this. So if y is between 0 and t, then fy, that is dy over dt, is negative, right? And the negative means because the graph is below, so it will be negative, means y is decreasing. Between t and k, it is positive, means it will be like this, right? And greater than k, it will be negative. So it looks like 0 is stable, right? It looks like 0 is stable, and then because you see that it will, if you continue, it will look like that, right? Because it will be positive. So it is stable, this is unstable, and this is stable, right? So you see that y star equals to 0 and kr stable, right? Stable, asymptotically stable, right? And then y star equals to t is unstable. So you can check the stability by finding the derivative of that and plugging in 0, k, and t, okay? So now what I want to do next is I want to plot y versus t, okay? So if you plot the y versus t, this is what you will get. So because this is t, this is y, right? This is 0, this is threshold t, this is the carrying capacity k, right? So this is the carrying capacity k, and this is the threshold parameter t, okay? So if you start with the value that is less than t, then this will go like this, right? So it will go like that, right? It will go like that. If you start between t and k, it will go to the k, right? Because see, it will start between t and k, it will go to the k. So meaning that you see that, right? It will be like this, okay, and like that. Now if it starts above k, then it will go to the k again, right? So this is what you see. So this is stable, because from both sides it is, if you start close to k, below or above, then it will go to the k. This is unstable, and this one is stable. So this is the qualitative behavior of the logistic growth with the threshold. So let me do some of the examples from the book, okay? So let us see that this differential equation, it is also called the Gompertz equation, okay? Gompertz equation. So how that behave, let's see that. So if y is less than k, what happens? If y is less than k, k over y will be greater than 1, right? Greater than 1 means natural log of greater than 1 will be positive. So this whole thing will be positive, meaning if y is less than the carrying capacity, then the population will, the derivative will be positive, so the population will grow. If y is greater than k, this will be less than 1. So natural log of less than 1 will be negative. So in that case, dy over dt will be negative, so y will decrease. So it behaves similarly as a logistic equation, okay? So this behaves similarly as a logistic equation, but usually this Gompertz equation is used for the tumor's growth, okay? Tumor growth model, all right? So it shows similar behavior, but the nature of the curve will be little bit different. The nature of the curve will be little bit different there. If you draw the graph of this, okay, I can show you that. Okay, so this is the this is basically the direction field for the logistic equation. I took r equals to 0.5 and then k equals to 30, okay? So if I draw any curve, look at that, they are quickly going to the going to that carrying capacity. You see that? So they are all going to the carrying capacity. Now, so if I do this for the Gompertz equation, you see that natural log of 30 divided by y, right? If you do that, how that look like? So let us look at this. So this is the Gompertz equation, okay? So if you see that, it is almost showing the almost similar thing, but you see that the nature of this concavity is a little bit changed, right? So this is the Gompertz equation, but you see the similar patterns in the Gompertz equation and the logistic equation, okay, guys? All right. So I want to solve this equation. So it looks like it is an autonomous equation. There is no t. So since there are y and k over y, I think we can use the variable separation, right? What you can do is you can do 1 over, to solve 1 over y times natural log of k over y, right? Dy equals to r times dt, right? Now I want to integrate this on both sides. So how would you integrate the left hand side? I think you need to use the u substitution, right? Let u equals to natural log of k over y, right? So what is du over dt then? Dt, it will be 1 over k over y times negative k over y square, and then times dy over dt, right? Because we are finding the derivative with respect to t. So what do you get? So if you do that, then you can actually cancel that y and 1 of the y square, k with k, right? So this will become, basically what you get is there is one y left, right? You see that this y will go there, so you can write, so what is left there is du over dt equals to, you can write this as negative 1 over y and then dy over dt, right? So basically in the differential form, you can write du equals to negative 1 over y and then dy, okay? So what you get here is, so this is u, right? This will become u because we assume that this will be u. 1 over y dy will be negative du, right? Because there is a negative 1 over. So what do you get? Therefore, hence, you can write hence, this will become negative du over u. You see that? Because this one is u, 1 over y dy. 1 over y dy will be negative du equals to, what is the integral? It will be RT plus C, right? This is what you get, RT plus C. Now let us integrate the left side. So this will be negative natural log of u, okay, equals to RT plus C. Now what would you do after that is, so if you continue, what do you get? You get natural log of u equals to negative RT minus C, right? So I'm just multiplying both sides by negative 1. So I want to get rid of the natural log. You get u of t equals to e to the negative RT minus C, right? Now using y at 0 equals to y0, we get, what do you get? You get u0 equals to, you get e to the negative C, right? So e to the negative C is basically the u0. But what is u0? So u0 will be basically natural log of k over y0, right? Because y at 0, which is y0, that's the value of e to the negative C. So how can you write this one then? Thus you can write u at t is equals to, what do you write? You can write e to the negative C times e to the negative RT, right? So this can be written as natural log of k over y0, that is e to the negative C times e to the negative RT, right? What is on the left side though? You have natural log of k over y, right? That is ut, I'm replacing back, equals to natural log of, you can write k over y0, right, times e to the negative RT. Now we want to solve for y. So what I want to do is, I can flip-flop this. How do I do that? Because you see that there is a properties of the log. You can write natural log of, let's say natural log of x can be written as, you can write natural log of 1 over x to the negative 1, right? I'm just move big if x is for any x, right? So you can do 1 over x to the negative 1, which can be written as natural log of 1 over x to the negative 1, but this can be written as a negative natural log of 1 over x. That's what you can do, because this comes to the front, right? So what I'm trying to do here is, I want to just, if you flip-flop that thing, if you write the reciprocal of that thing, then there will be a negative sign in the front, right? So you can write that one as, you can write negative natural log of y over k equals to negative natural log of y0 over k times e to the negative RT, right? Now you multiply by both sides by negative sign, you get, therefore natural log of y over k is equals to, that negative sign cancel out, so natural log of y0 over k times e to the negative RT. Now let's solve for y. So you get, therefore let us remove this natural log on the left side. You get y over k, okay, equals to, this is equals to e to the natural log of y0 over k times e to the negative RT. That's what you get. And then therefore y of t equals to k times e to the natural log of y0 over k, and then times in the exponent, okay, e to the negative RT. So this is inside the bracket. So this is the final solution for the Gompertz equation, okay.